My pleasure to welcome you here today to this lovely venue. We're all getting used to it and being spoiled royally by it. We've got a really, I think everyone will agree, we've got a great lineup of lectures today. There's something here for everybody, I think. And I'd like to take the opportunity to say thank you to Sarah and to David for putting together such a great collection of lectures for us.
I will now introduce Robin Osagie. Okay. Robin is Business Development Manager at EXFO. Robin has 20 years experience in the service assurance and service fulfillment domains of the operational support systems industry. After leading both solutions architecture and product management teams across the industry, Robin is the Business Development Manager at EXFO within the Service Assurance Division. So, Robin, it's all yours.
Thank you. Okay, so this is the last session before the AGM, and I guess more importantly the cocktail. So I'll try not to keep you too long. So what I'm going to talk about today is ecosystem modeling and data integrity, and specifically modeling of the networks, the services that run on top of those networks, and also the customers that are using those services. And this is really key in not just fulfillment and planning activities, but also assurance activities, okay, across the infrastructure for a service provider. But before I start, I want to take a quick poll. So how many of you, if you can raise your hand, just let me know how many of you came here via the tube today? Okay, so there's quite a few. And how many came via the tube but also live in London? One. Okay. All right. So I guess for those that did come in via the tube, at some point you would have come across this or interface to this. Okay. And so this, the London Underground map, is effectively one of a prime example of a topology model. Okay. And because of its existence and its accuracy, we pretty much take for granted how easy it is to map out our journeys from one part of of London to another part of London. Okay. If, for example, we were trying to go from, let's say, Leicester Square, or from London Bridge, and we were trying to get to Oxford Circus, and we knew that there was a signalling problem, for example, in Leicester Square, we would know that whether that problem was going to impact us or not, effectively because we have a model of that network and how everything is actually set out, and from a topology perspective, how everything is interconnected. But now, imagine if we didn't have a topology, we didn't have a map of that. Trying to understand how, for example, we would model or how we would actually navigate across the infrastructure, across the actual city would be pretty difficult, okay? If, for example, there was a problem anywhere, well, you wouldn't know whether it was going to affect you. But then if, for example, you lived in London, you might be more familiar with that particular journey and the specific areas within the specific lines and so on. Maybe you travel the Northern Line on a daily basis, you would understand, well, how to get from point A to point B. The key thing is, if you have an understanding of that domain, or an understanding of your route, then you'll understand how to navigate across the network. But if, for example, you wanted to travel to another part of the city, well, you'd effectively be blind in terms of how you need to navigate to that point. Okay? And this is effectively one of the key issues that we face in a lot of the networks that we're managing today. Most CSPs don't really have an accurate visualization, topological visualization across the network, from the physical and to the services, the logical entities that run on top of that. So to an extent, in a lot of instances, we're blind when it comes to things such as impact analysis. Let's say a fiber or a node goes down. How do we understand what customers are going to be impacted by that? Or, for example, if there are a number of areas or a number of sites that are degraded or failing, how do we understand what potential fiber or what potential trunk could be the root cause of that? Okay? And so why is, modeling this information such a challenge? The problem generally is rooted in the siloed approach in which we plan and manage our networks today. So, as an example, often the people that are working in the access part of the network don't really work that closely with the people that are working in the core. People that are working, for example, on DSL and fiber, there's a number of different silos in the way that they both deploy and manage and assure those networks. And there's an even larger chasm between the people that are working from a network perspective and those that are working in the customer side of things. So understanding customer data and services, it's generally different parts of an operator that are working on that. And those silos effectively create multiple different repositories of information which are not interlinked. And this is effectively what causes some of these issues around trying to address that. Okay? And now with mergers of a number of big different network companies, BT, EE as an example, you've now got lots of different infrastructure stored in different, and information about that stored in different systems, but trying to get a picture across all of this becomes a real big challenge. And one of the biggest challenges for this is effectively the way that we model these data today. So in traditional systems such as inventories or configuration management or CMDBs, the primary technology used is relational databases. Okay? And relational databases, or data warehouses, are not particularly efficient at modeling network information. So don't get me wrong, I mean, relational databases and data warehouses do have a strong focus on things such as if we wanted to understand aggregation. So let's say how many people were in this particular session today, aggregate that, and then understand, well, how many people were in the previous session and see how that trend changes over a period of time, then a relational database is a good place to store and manage and model this type of information. But if, for example, you wanted to understand, okay, take yourself and then understand, okay, well, how am I connected to the person that I'm sitting next to here in this session today via LinkedIn? And then perhaps I want to build a map of how everybody in this room is connected. Well, a database isn't a good way of modeling that. Okay? The key thing is that when the concern is about the relationships of the data itself, as opposed to aggregation information of the data, then databases aren't a good way of modeling this. And when we're modeling a network, we're effectively trying to model the relationships between different entities. Okay? And we were looking at the tube map, but in a network, but the tube map is effectively one layer. In a network, there are multiple layers. Okay? You've got the physical, logical, services, and so on. So it's obviously a lot more complex. Okay? And so there are technologies, or newer technologies, that are out there. Hadoop, or big data, is quite a common term and a big buzzword now that's often used by a number of different operators to effectively try to address the siloed mentality. So with big data, things such as Hadoop, you can get a significant amount of data and store it in a single place, in a single cluster. The problem with that is that although you've got all of the data in a single place, you're not actually addressing the relationships and how that data is correlated and how that data is linked up. Okay? So you might have the data in a single place, but you've still got the issue of it's not linked up. How are the different connections and the relationships across that information? How does that instantiated? So there are additional technologies graph technology that are a lot more suited to this. Okay? One of the key things with graph technology is that the relationships associated with the data is inherently stored within the model itself. Okay? We don't have the concept of tables and so on. I'll come on to that in a second. But this kind of technology is used in things such as social media. So Facebook, as an example, where you have one person who may be a friend of another person, who's a friend of another person, and so on and so forth. That web of connections is effectively a graph. Okay? So, trying to understand the difference between relational databases and these semantic graph models. Well, one of the key things to bear in mind is that in a database, the model and the data that you want to store in it are quite tightly coupled. So, specifically, you effectively have to understand what the data looks like before you can load the data into your system. Okay? And so once you have done that, then you'll be able to load the data into the system and everything is working okay. Problem comes is that oftentimes you'll have another use case or some other kind of data that comes along, and when you try to load that into the platform, then it would fail because perhaps it doesn't match or meet or map to the model that you've already created. And so then you have to go through a process of trying to update your model or schema in a database to try and fit this. Okay? That process is significantly onerous and time-consuming, and it's one of the key reasons and the key challenges to traditional inventory approaches and things like that, trying to get all of this data from multiple systems into a single place. Okay? Now, with the semantic approach and the graph technology, you don't have the concept of having to create a model up front. You effectively can bring in all of that data and then overlay models logically using business rules. Okay? And so one of the analogies we use is that the models are a little bit like a lens looking on top of the data as opposed to a container that needs to store the data. So because you've got a lens looking at the data, there are multiple different models that you can create. Changing the model is simple. So it's really easy to start to understand how the different information is linked together, and as additional different use cases come along, well, you can quickly create an updated model logically on top of that and visualize the data through that particular model. Okay? So here is a very simple representation of some data as it would be stored in a database and the equivalent in a graph. Okay? So this is a pretty rudimentary 3-column table. So you've got a customer name, status, and a product, John Smith, product, and broadband XXL. In the graph, as opposed to having these columns and rows as you would in a database, we have the concept of a node, a link, and another node. So 3 entities, node, link, node. Everything is effectively stored as a node, link, and a node. So that first node here would be John Smith. Importantly, we model this link. So the link in this instance is has product. The last node here is broadband XXL. So this piece of information here is John Smith has product broadband XXL. Okay? That we call a triple. Okay? So you have multiple different triples. So for example, here you've got broadband XXL is a product. John Smith has status 1. John Smith is a customer. The key difference here is that the information about how the data is connected is a first-class citizen of how we represent this data. So we can see how, for example, this particular node links to this node. That information isn't inherent in a database. You effectively have to infer it in one way or another. Okay? And this is one of the key differences. So I mentioned the triple, which was the node, link, and the node. The real name for that first node is the subject, and that's the thing you're referring to, such as John Smith. The predicate, which is the link, and that's a property associated with that subject, so has product. And then the third thing is the object, so the value of the property. So in this case, broadband XXL. The subject and the object can also be interchanged. So for example, broadband XXL can be a subject, in this instance is a product, and is the predicate, and then you've got the object over here. Okay? And so if you want to expand the data effectively expand the model of the network, then we effectively just add more triples. So here we can add, for example, John Smith has billing address, 1 London Bridge, and John Smith has an address, 65 King's Cross Road. And so by adding additional data to the graph, we start to build a larger network of that infrastructure. And so it's the same thing that will be mapped not just to some customer information, but across the whole network. Okay? And then the key thing is here we can start to ask questions about the data. So for example, try to understand or run a query which would say which customers have got 2 addresses, for example. In this example, you have 2. And so you might think, well, perhaps that could be an error, that they've got 2 addresses. But then it could be a situation where you have a landlord use case, whereby John Smith lived at this particular address, but his billing address is over here. So he's actually rented the property out, and so he's got a billing address, the bill goes to another place, and a tenant lives at this particular point, and this is where the service is being sent to. The key thing is that multiple different use cases don't require you to go and change your physical model. You can just extend the graph and further explain that and model it. So looking here, we've got some information that perhaps would come from a customer relationship management tool about this particular customer, John Smith. And let's say if John Smith also had another service, and so was also in another customer relationship management tool, we may be represented here in the second tool. Now, we've got 2 different tools, 2 different systems, 2 different sources of data which are managing the same customer, in this instance, John Smith. In the first system, he's called John Smith. In the second system, he may be called John H.S. Although effectively it is the same customer, they've been managed and mapped in 2 different ways in 2 different systems, which we somehow want to correlate together. Now, it's a lot easier in a graph because what we can do is by having other attributes associated with that customer, we can then infer that actually, based on the fact that they've got the same ID and so on, we infer that actually this is the same customer. So you can collapse that from a graph perspective. Okay? Now, if we expand that, because there's a simple inference there showing that, let's say if we had some information in an order management system related to John Smith and the service that John Smith had. So here, for example, in the order management system, broadband, it's called broadband 100 meg, there was an order with an ID, which is 2468, and it's installed at this particular address. Now, what we can do here is, again, by using the graph, we can link this information together between those different systems. So the IP address is the same. We can use rules which dictate that that can be linked together. And then we can also see that here, although the addresses are different, so in the order management system it says King's Cross Road, but in the actual CRM it's 65 King's Cross Road. So here in the order management system, there effectively is a data integrity issue there. Okay? So it's somewhere along King's Cross Road, but you don't know exactly where. But because we're able to link this information using the graph, we can effectively infer that this particular address should be 65 King's Cross Road. And so you can effectively then update this system, the order management system where this data came from, with the information that we've now inferred from other systems that we've interconnected. And so this starts to bring us on to data integrity, which is quite a key issue and key challenge across pretty much all CSPs today. Okay? And data integrity is an issue because there are multiple different systems which represent information about the network but are stored in different places. So for example, you may have an inventory system which represents the network. You may have a planning system representing the network. And in some cases, you've got multitudes of these different systems. And now because these systems are being updated, often in silos, trying to get them to link and associate with each other becomes a challenge. And this is where a lot of these misalignments come from. Okay? And these misalignments are central to a lot of process failures that we see across the service provider. Whether it's things such as customers being incorrectly billed, based on some misalignments in the billing system compared to what may be in the provisioning system, which may compared to what may be in the CRM platform. And then, for example, where the deployed network is misaligned from the plan or from your planned network. Okay? And this is quite an important one because this often leads to a lot of things such as potential outages, where you may not have the main and protection lines and things such as that supporting certain customers, or different sort of different entities which are supporting the network accurately based on how you wanted to plan that network. Okay? And so when you have things such as, let's say there's a problem or there's an outage, trying to now, you often will have like a war room where you may need to have some people from the access network, from the core network, all brought together to try and understand how everything is linked up, to try and now figure out where this problem could be rooted from, trying to understand the root cause of the problem. And that's essentially because these systems aren't joined up. There isn't a central view across everything to illustrate, well, if there's a problem here, it should be linked to this thing over here. And hence why you have these war rooms. Another issue is customer frustration, service provisioning and management. So, for example, when a customer has an issue and they call into the service provider, one of their biggest frustrations is when that service provider doesn't understand or doesn't know about the specific services that they have. Or if they've got a problem that they've logged previously and they call again, they don't want to have to go through that problem and detail it out again to that same person. That causes frustration. And the issue with this is because of data, effectively. Data not being stored and mapped across the different platforms that service provider has. It's managed in silos. The person that answers the phone uses a CRM system. If that CRM system isn't linked accurately to the network and perhaps some alarms and faults that are going on within the network, then they're not going to be able to proactively tell that customer once they call that actually when I type in your name, I can see that there's some issues in the network that affect you. I know, for example, by linking in the plan maintenance work system, that somebody's going to be sent out to go and fix that at a particular time. If you're able to link all of these systems together, you're able to start to address these things in a more proactive way. Okay? So, addressing data quality and data integrity. So, I guess really in any data integrity and data quality problem, one of the key things that you have to understand and importantly model is the source of truth. And generally within a CSP, the source of truth is the network. So if you have an accurate model of that network, you can then start to use that to correlate and understand any discrepancies that you have between, be it your planning systems, your inventory platforms, order management, and everything else that goes across that. And by bringing in information from the network, normally from your element managers and network management systems, you can start to build that information and start to correlate and understand how all of that data is linked together. Okay? And the key thing is that you need a flexible capability to be able to model this and model it quickly. Okay? And as I've been mentioning, graph is an optimal technology for doing this. Okay? Because if you think about it, a graph, as we mentioned before, is based on nodes, links, and nodes. And a network, effectively, are different entities with a different link and a node at the end. Whether in fiber, it's an OLT, fiber, connected to an ONT. In a RAN network, you may have an RNC connected to an IUB and then a node B. And the same thing with a microwave network. 2 microwave dishes and a microwave linked in between. You've effectively got nodes and links. And so using graph technology, it maps far more accurately to the way a network actively is instantiated, as opposed to trying to take that network and then map it into a database. Okay? But one of the key things with data integrity is that the data integrity process needs to be owned. And commonly, data integrity as a process generally isn't owned by anybody. Okay? It's almost like a secondary thing that needs to be done to support the network itself, to support operations as a whole. But really, to address this, a data integrity team and process needs to be instantiated. And that process needs to be, as I mentioned, defined, but also prioritized. It needs to become a key thing within an operator, that data integrity is in the heart of a lot of the things we do, be it from digital transformation to fulfillment activities and assurance activities. And that process also needs to be able to be flexible, such that when things need to change, then we can manage that. So looking at that process, some of the key things that need to be addressed. So first of all, we need a method by which we can find these discrepancies and surface them. Okay? Using graph technology, it's quite easy to model the network and see where there are discrepancies between the network model and the model in your planning system or in your inventory system. Taking that, comparing them, and then we can quite quickly display and understand the discrepancies. But once we've got those discrepancies, we need a process by which we can go and correct those systems. In some cases, this can be done automatically. So when you find a discrepancy, we can write back into the source system, be it a planning system or an inventory, directly into the database and update it. In some cases, and in a lot of cases, those systems don't allow people to actually go and directly update them. So in that case, we can output files which can then be managed by people to go and update those systems. But what's important with that is that those manual corrections or those files need to be assigned to owners. People need to buy in to the overall data integrity and data quality process. Okay? So where there isn't any automation directly up into a database or into a system, you need to be able to take that information, associate it with people, assign it to people, and then via workflow, have them go through a process of updating those systems. Okay? And then you need to also be able to track that. Okay? So track how we're improving data quality. Okay? So that it becomes visible and it becomes more of a process that people can effectively buy into and start to see the value of that. Okay? So tracking things such as improvement and things like that is quite key in helping support that. And then finally as well, one of the key things is effectively not just having people assigned to it, but they need some kind of motivation to be able to want to actually go and update that. So in some cases, trying to gamify the process of, this team has improved data quality across their systems by a certain amount, for example, compared to these other teams. It really does need to be a process whereby data cleansing and data quality management is a key aspect of the overall operation within an operator. Okay? So, to summarize, the key thing we need to look at is rethinking our approach to modeling and prioritizing that within a CSP. Traditional techniques, using databases and so on, they exist, but they're not efficient. And this is why we often have multiple different systems which represent the same pieces of data, but are inaccurate to what's actually deployed within the network. Getting an accurate view across everything supports not only fulfillment processes from planning and provisioning, but also assurance and transformation, digital transformation. Digital transformation effectively requires you to automate a number of processes. If you want to automate these processes, the data in those systems that you're automating across has to be accurate. Otherwise, the process will fail at one point. And Vanessa was just talking about 5G now. So with the new technologies that are coming into play, 5G and IoT, we're going to have a lot more devices and a lot more complicated network. So it really is important to start to get an understanding of that topology now, because the problem's only going to get worse as we add things such as virtual networks through things such as NFV and SDN and so on, where the network is going to be changing a lot more rapidly than what it is today. Okay? And lastly, ownership of data integrity as a process. It's a key process that we need to bring in to operators and manage and own as a central part of the day-to-day activity. Okay, and that's it.
That's absolutely excellent. And that actually gives us time, if anybody wants to question any of the previous speakers, And now's your opportunity.
And a lot of telcos that I've come across in their BSS and OSS systems, that they often suffer from chronic stovepiping, and I wonder if this approach can help to uncover data integrity issues in a stovepipe architecture. It's not really an architecture if it's a stovepipe, arguably. But.
So I mean, the answer is yes, effectively, because the key thing that we're doing with this approach is to model the infrastructure. And it's not just the infrastructure from a network perspective, but customer infrastructure. So let's say an example of where you may want to decommission old equipment, moving customers from old equipment to new services and new equipment. To be able to do that, you have to understand which customers are connected to the perhaps traditional or legacy equipment. So being able to bring all of this information together, linking it up and modeling it, provides that visibility. And that's across both BSS and OSS. But the key thing is because the fact that we say BSS and OSS in itself is siloed, which kind of goes against the way that we really need to model and manage these things, because everything is connected in one way or another. And by having these silos, you're going to have these issues where you're blind to certain impacts of things that are happening in the network towards your customers. So it's really a case of starting to get that end-to-end view and managing things end-to-end across the operation.
You talked a little bit about your system as if it's overlaying and sort of monitoring other systems. Can it be used as a primary data source?
So yes, it can, but generally the key thing that it does is it's bringing in data from multiple systems and linking it together. You can also use it as a primary source for process, be it some kind of workflow process and things like that. But the key thing is not actually to remove all of the systems that you have, because let's say you've got performance management over here that's got KPI information, you've got alarms information over here with fault management information, and you've got the network itself, planned maintenance, trouble tickets. All of this information in one way or another is linked. So rather than replacing those systems, it's a capability that enables you to associate all of this information together to support both assurance and fulfillment type activity.